Good morning to everybody. I'm Antonio Costanzo from INRIA, which is the French National Institute in Computer Science. The co-author of this work is Valeria Loschi, which comes from the same institute. In this work, I will give you some details about our visible light platform we developed using GNU Radio and the Universal Software Radio Peripheral by National Instrument. For developing this system, we used a software-defined approach. This is the outline of our presentation. After a short introduction on visible light communication in general, I will provide you some details about our architecture, the components we used, and its implementation. At the end, I will introduce some possible applications which could be developed according with our system. For example, I will show you the implementation of the full duplex system, which allows the possibility of adapting in real time some communication parameters, like for example the power or like the modulation index. These aspects are really interesting for the development of the visible light paradigm in real applications. So, what is visible light communication? Visible light communication is a subset of optical communications. Like all the techniques which use light, which is the portion of the electromagnetic spectrum that we could see with human eyes, namely in the range between 400 and 700 nanometers. For example, in optical fibers, light rays are driven in some structures, while in laser there is a powerful and narrow beam which is produced for allowing the communication. In the visible light paradigm, instead, we use normal LED lamps, not only for communicating, but also for transferring data. In this way, we could dramatically decrease the cost of the communication in terms of device and in terms of energy. But what are the main motivation for using VLC? Visible light communication has raised the interest of scientific community, especially in last 10 years. The main motivation is due to the spectrum scarcity. In fact, radio frequency spectrum is being more and more crowded and more expensive. The use of the huge optical spectrum could allow to solve this issue, allowing a sure, cheap, and high data rate communication. Another important aspect is due to energy efficiency. In fact, we could use lighting infrastructure, which already exists everywhere, for communicating data without additive costs. Because we already have this infrastructure, we fed them anyway. But and there's another motivation, because even if there are not sufficient studies for demonstrating the damages of radio frequencies to human body, clearly light could represent the most natural and safe source of energy, since human body has been adapted to light power since it's born. There are lots of possible realistic scenarios in which we could employ visible light communication. For example, in hospitals, in hazardous environment, like for example, petrochemical plants, or mines, or aircrafts, where the radio frequency waves are forbidden or strictly limited. Because, for example, they could interfere with critical devices, or they could cause accidents, like, for example, interacting with chemical substances. There are also some interesting outdoor application. For example, a nice application could be the underwater. Because radio frequency waves do not propagate properly in the water, while light propagates better. Another interesting application could be the vehicular application, where car light could be reused for allowing vehicles to communicate each other. But especially in the latter case we saw in the slide before, speaking about outdoor application, there are some issues. In fact, different from laser or optical fibers, VLC exploits low power energy with wide light beams and often in an uncontrolled scenario. This causes two big issues. The first one is the high signal attenuation, and the second one, especially in outdoor scenarios, is given by the huge interference of either light source, namely the sunlight. Since this latter problem is really tricky to solve, so the efficiency of classical noise techniques we use normally in radio frequencies is really limited. Some novel techniques could be used. An adaptive system where we can change some communication parameters accordingly to the scenario could be really attractive for this kind of protocols. But however, in order to have adaptive system, we need a feedback network. And there are very few studies on adaptive VLC. And most of them are not experimental, they are just carried out with simulation, because there are several issues in building a feedback network, and there are some other problems with synchronization, with uplink and downlink interference, and we tried to solve with our architecture this kind of problems. In this part of the presentation, I will give you some more details about our architecture, the device which is composed of our architecture, and the main operation which are supported. Now, before starting our discussion, in this slide I reported some of the possible signals which could be modulated using an LED lamp. In the first case, for example, we have amplitude modulation, which associate to each level of the signal a different amplitude. In the second case, we have the pulse width modulation, which increase or decrease pulse duration in base of the signal level, and pulse position modulation, which modifies the position, in this case, of the pulse in a slot of fixed duration, which codify a symbol. In our work, actually, we don't use all the three modulation, but we just use the PAM, so the pulse amplitude modulation with different indexes, so 2, 4, 8, and 16 PAM, and the pulse position modulation, so 2, 4, 8, and 16 pulse position modulation. In this way, we can show a faster communication, so mainly a PAM with a high index, or a communication which is more robust when there is more noise. For example, a pulse position modulation slower, so also in this case with a high modulation index, for example, a 8 or a 16 ppm. This is our proposed full duplex architecture. So in this block diagram, in the left part, there are indicated the main device which compounds our full duplex system. While in the picture, there is our setup, which is located on the table of my office room at IRIA. We consider a main optical communication, so the main optical flow of data, which allow the communication of user data from the transmitting PC, which is the one on the left, and the receiving PC, which is the one on the right part of the picture. And we also consider a feedback communication in the reverse path. In this case, For the feedback communication, we consider just the sending back of some control messages. We use a gigabit Ethernet for connecting the PC and USRP, and the USRP manage the signal control processing related to the main optical communication. While some Arduino One devices, you can see in the back of the photo, they are used for controlling only the feedback channel. So the most important part in each optical system is the optical front end, which in this case is composed by an LED, which is a Cree LED of 15 watt, with a maximum light flow flux of 1000 lumen, and a big field of view of 120 degree. And we use also a LED driver, which allow to modulate the signal, which is composed by a single stage amplifier, a BST, which is important for allowing the system to work in the correct dynamic of the USRP, which is between -1 and 1 volt, and without wasting power, because otherwise with the single LED we lose the half of the power that we can manage. And we use a 12-volt power supply for feeding the LED. The main optical channel we considered in our experimentation are some indoor scenarios, like the one we already show in the other slide, which is an indoor scenario without particular disturbs or interference. But we also considered something like outdoor scenario. Actually, the one I show in the other photo is not an outdoor scenario because it's out of the window in my room. But in this case, we have the system which is solicited by sunlight and other optical interference coming from the external environment. Another important part in our circuit is the receiver optical front end, which in this case is composed by a centronic photodiode, which is a commercial photodiode characterized by an active area of 15 square millimeter, responsivity about 0.2, and with a bandwidth of about 30 megahertz, so it's enough for our operation. It's more or less the same of the LED driver. And we use a transimpedance gain of about 1 megaohm, so a very high transimpedance gain, which is necessary for amplifying the few current provided by the photodiode. Here we have the USRP, which is a device we use for allowing software-defined operation. Namely, we use software-defined operation in order to have more flexibility and to decrease the cost of hardware, because most of the operation we do in software. And we control them with GNU Radio routine. So we use in this case a USRP 2922, which, as we said, -1 volt input-output signal, and has a 20 megahertz bandwidth. But in this case, since we use very low frequencies for modulating the signal of the LED and the signal received by the photodiode, we integrated the two daughter boards provided by Ethos in our system, which allow to manage the operation in a low frequency range between 0 and 30 megahertz, which matches with the frequency band from our modulated signals. And after we have a receiver PC and a transmitter PC, which exchange user data and exchange also the control data. And for this for this scope, we use GNU Radio 3.7 and Python 2.7 on a Windows 10 operative system. Clearly, the same operation could be done probably easier with Linux. and use a psharm IDE in order to provide the routine that after we use it in the proper Python blocks. We can manage up to 4 megahertz sample rate using 2, 4, 8, and 16 pulse position modulation and pulse amplitude modulation. So we use some ad hoc Python blocks for allowing a serial communication between the PC, so the new radio routine, and the Arduino, which provides the communication and controls the communication in the feedback optical channel. So we need an exchange of data between new radio and Arduino, and we do it throughout some Python blocks. After this communication is a standard serial I/O communication of 115K. For the optical channel, in the feedback case, we don't need a very fast communication, so we just use an on-off keying with a Manchester recording, which has about 2 kilobits per second, because Arduino is not a very fast way to exchange data. And we just send one printable ASCII character for each control message. Normally here we are using general characters, so we didn't specify the meaning of each character, but each character has means a control message. We use the same diode and the same LID for the optical front end, but we didn't use amplifiers and BST, because in this case, with the Arduino, we can manage power up to 5 volt, and not just from 0 to 1 volt, so we don't need to amplify the signal, and we don't need the BST for achieving the right dynamics of the Arduino. And we just used, for this first implementation, some black paper box around the devices, around the receiver devices, in order to avoid the coupling between the main channel and the feedback channel. So in these last 2 slides, I provide 2 examples about how our system could be employed for allowing some adaptive operation in a VLC architecture. Since the content of the control message, as I just said, is general, lots of other possible applications could be envisaged. But in this part, we just focus on 2 possible applications that we are already developing in our activities. In this first example, I show you how we intend to use our system for obtaining an adaptive modulation control. In particular, the kind and the order of modulation could be set in real time in order to match some changement in the scenario. If we look at the table in the right, we see how, based on a threshold mechanism, if signal-to-noise ratio improves, so we have a channel without a lot of noise, we can use faster modulation, like the 8 p.m. or the 4 p.m. While when the signal-to-noise ratio is poor, we move to more robust modulation, like 8 ppm or 16 ppm. In this system, we need obviously an uplink channel for communicating back to the transmitter the information about modulation control. So input data are modulated. They are sent to the receiver, which estimates signal-to-noise ratio. Further perform also a noise mitigation, they modulate the data. But at the same way, the receiver decides, according to the criteria in that table, the next modulation, which is communicated back to the transmitter using the feedback channel. Now, we have already implemented this system using the same architecture, but a different software control. And this paper could be found in the reference I give you that we write in the collaboration with the Professor Mario Biaggi of University of Sapienza in Rome. A last example in which we are currently involved is an adaptive power control, which increases the power when the transmitter and the receiver are far away each other and decrease the power when they are close each other in order to save power for avoiding some saturation effect when the transmitter and the receiver are too close to each other. In this case, we can always use signal-to-noise ratio for understanding what is the power that the transmitter should use. And also in this case, we can communicate it through the feedback network in order to reduce the power delivered during the communication, for example, with the logic we can see in the table, and we just associate a binary message, so an hash character, for each transmitting power. So in this case, we can reduce the power during the communication. It could represent a critical aspect, for example, in lots of applications, like in mobile devices, which are equipped, for example, with a small battery. So, for concluding, in this brief presentation, I show you how we have designed and implemented a complete bidirectional system which is based on universal software radio peripheral and using some commercial LEDs and photodiodes, so in a very low-cost logic, but which are able to receive and send back messages on a dedicated channel. We applied the software-defined approach, which is based on GNU Radio signal approaching. And we implemented, always using GNU Radio, an architecture which is able to receive and elaborate feedback, exchange information, which will potentially allow to make lots of control operation for adaptive purposes. So improving the possibility of using visible light communication in a real scenario. So in our current activities, we are implementing the architecture we already proposed in the reference, but using GNU Radio environment. And we are designing and implementing also other algorithms for power transmission control, like the one that I showed you in the last slide, but also something of more sophisticated. And we we want to implement some other novel techniques of signal synchronization in order to improve our system and also other modulation schemes, for example, mixing PIM and PPM in the same system in order to increase the performance in terms of rate, but also in terms of noise robustness. So this work was supported by the region Hauts-de-France under the framework of the project Stimul. So the presentation is finished. Thank you very much for your attention.